So today I'm going to tell you about the circle packing theorem. And this is, and if you had too much to drink and is very hungover from yesterday, then this is great for you because you can only listen to the statement of the theorem and then go to sleep for the next hour and a half, and you will be perfectly fine for the rest of the class. So I'm going to state the theorem and then tell you some things about the proof of it. The proof, when I taught this proof one time, it took me 2.5 hours, and this time I'm going to dedicate 1.5 hours. So I will skip some parts, but it's completely elementary proof, and it exists. It's written fully in the lecture notes. So the circle packing theorem. Right, is stated as follows, right? It's of course due to Kebe, but this is a slightly more modern proof due to Bill Thurston. And it states that any planar graph, as we saw, can be represented by a circle packing. So let's see, any planar graph G, for any planar finite simple planar graph on vertices, let's say V1 up to Vn. Sorry, I'll try to speak loudly. You have n vertices. You have a planar graph. Then there exists circles in the plane, disjoint circles. C1 up to Cn, such that, so they have disjoint interiors, disjoint circles. I guess I mean that the inside is disjoint, but the circle themselves may intersect, such that Ci is tangent to Cj if and only if Ij is an edge of the graph. Okay, and of course here's the basic, perhaps the easiest or second easiest example. You have 3 circles like that, and these 2 are supposed to be tangent. It's always hard to draw these things. There's a slight distinction between a planar graph and a planar map that I address in the notes. A planar graph, as we stated, is a graph that can be drawn in the plane in the proper way so that 2 edges do not intersect. And in many cases you hear the word planar map, and they're almost the same. A planar map includes further combinatorial information about how exactly you draw the graph. So for instance, this planar graph, right, on 5 vertices is not equivalent as a map to the graph that is drawn like this, right, with this with the vertex inside. Okay, so but it is equivalent if I replace this edge instead of a straight line by doing something like this. So a map is also a combinatorial object. It doesn't contain the drawing itself, but it tells you which drawings are allowed up to deformation of the edges, right? So, and the way to think about it is, I have the set, so it's an information, the combinatorial information that I have is the set of vertices and the set of edges, and for each vertex I have a cyclic ordering of its neighbors, of the vertices that it neighbors, or of the edges that touch it. And the cyclic order of the edges determines, what is the correct drawing. So if I call these vertices 1, 2, 3, 4, 5, here the cyclic order will be 4, 5, 2, and so on, while here it will be This is 5, 2, 4. Right here it will be 4, 2, 5. Right? So these things, the cyclic order of the neighbors is not the same. So these are different as maps, but they are the same as graphs. And the circle packing theorem stated like this can also be extended, and you see that this is indeed what will prove that it applies not only to graphs but also to maps, in the sense that the drawing will respect the map structure. So here, the first graph I will draw something like this, right? And the second one I'll draw as something like this, right? And these two drawings give you the same graph, but not the same map. Okay, and this is a distinction that comes up a lot, but but it's important to think so in many places a planar map is defined as a planar graph plus a drawing that is equivalent up to homeomorphisms of the edges and things like that. And this could be a little confusing, at least for me. But the best way, I think, to think about it is simply as the graph plus a cyclic permutation for each vertex, right? Then we understand it's a completely combinatorial information that we have here. Okay, so this is the theorem, and the second part of it is that it is unique, right? So in what sense is it is unique? Let's discuss uniqueness at the end. So of course, as we said, there cannot be absolute uniqueness, but if this graph is a triangulation, so let's write it: uniqueness. If G is a triangulation under the same conditions. So G has to be finite, planar, and simple. Right? Of course, you cannot hope to draw non-simple graphs with a circle packing, right? How will you draw a double edge? It doesn't make any sense. If G is a triangulation with an outer face so we think about the graph as having 3 vertices that are outside, 1, 2, 3, and everything is drawn inside, and it's a triangulation. Right? Something like this. So if this is the graph that you're starting with, with an outer face v1, v2, v3, then the drawing is unique. For any up to translations, rotations, and reflections, for any choice of radii for the three circles, right? So you can choose any 3 positive numbers to give that will be the radii of this vertex of v1, v2, v3, and there exists a drawing that is unique up to translation, reflections, and rotation. It is unique up to translation, rotation, and for any choice of radii for v1, v2, v3. Okay, so this is the uniqueness statement, and again, it's not surprising that if you know something about Möbius transformations, you have 3 degrees of freedom here, right? 3 choices of the radii to choose. Once you fix them, the map is essentially unique, and these are the same 3 degrees of freedom that you have in choosing a Möbius transformation. Okay, so what is any questions about the statement? So this is this is the statement that we will use, and you can forget about what you hear in the next hour and 20 minutes. Yes.
It's about the reflection. Doesn't it reverse the cyclic ordering or something?
That's true. You're right. So if it's a graph, then it's up to reflections. But if it's a map, then reflections are not allowed unless you are just in the triangle, right? And then Right? If you have only 3 vertices, then reflection is allowed.
Okay.
Yes. Right? If you reflect in the cyclic ordering of the inside vertices, or may flip the other way around. Right? So this is not allowed when you're in the case of a map. Okay? Any other questions? Yes.
If we take graph instead of map, there are not other degrees of freedom due to the fact that there are several map structures for one graph?
So it turns out that when you're in a triangulation, there's just one map structure, right? Up to reversing all the, yeah, up to reflections, right? It's not obvious, but you can show it. Okay, was the question clear? So in the case that your graph is a triangulation, the distinction between a map and a graph is much less important. Okay, so let's try and prove this theorem. Proof. So the first thing that we understand is that it's enough to prove it in the case of a triangulation. So it's enough to prove for triangulations. And the proof will use only high school geometry. There's not, even though Kebbe's original proof is much more complicated, but and the proof is in some sense an algorithm to how to find these things. And in fact, there's a lot of research done on like what is the optimal algorithm to finding and drawing these pictures. So if you look for circle packing theorem on Google, you'll find a lot of very nice pictures. It's enough to prove it for a triangulation, because if you have in your graph, right, you have here a graph, and inside there is a face that is not a triangle, right? Simply add a new vertex inside, right, and connect it to all of these vertices here. And if you know how to draw this, then you will have you'll have a drawing with the orange circle represented as the orange vertex represented as an orange circle, right? And okay, this is tangent, right? And then after you have the drawing for a triangulation, you just remove all the circles that you added, and you get a circle packing of the original graph. So it's enough to consider triangulations. So there's one thing that we need so now we're in a finite triangulation, right? I'm reminding you Euler's formula. Right, so G is now a finite triangulation. Right, so and I'm reminding you that in Euler's formula, the right, how does that go? A number of faces, V minus E plus F equals 2. Right? The number of vertices minus the number of edges plus the number of faces in your graph equals 2. Right? In particular, it shows that if you have a map of the same graph, right? If you have 2 different maps, they have to have exactly the same amount of faces. By the way, what is a face? Right? This is a relevant question, right? When we draw a graph, we're used to thinking about a face, right? As we take the drawing, right? The board is R2, and we remove whatever we drew, right? And we look at the connected components of the complement, right? Of these things, right? And sometimes we think about a face as the collection of edges that surround it, or of the vertices that surround it, or of the area itself in here, right?
Also the outer face, yeah.
And also the outer face. Thank you. Sorry, it's also a face, right? So sometimes it's easier to think about these things drawn in the sphere, but there's also a way to combinatorially define what a face is, and that is in some cases it's better. But to define it combinatorially, you have to be in the setting of a map and not a graph. So when you have a map, for instance here, right, and you have the cyclic ordering, how do you define what a face is? So you choose an edge, let's say 2 to 3, right? And you have a cyclic ordering on the edges that touch each vertex, and you arrive at an edge from 2. You arrive on this edge to 3, and you immediately take a right turn. What is a right turn? You simply take the next vertex leftwise or counterclockwise according to your map. So you go on this edge, and then you go on this edge, right, which you know how to do precisely because you have this cyclic ordering, and then you go on this edge, and the minute you return to where you started, you define these 3 edges to be in the same face, right? And this defines to you a face completely combinatorially, right? There's no need to draw the map, right, to say what a face is. You could just determine it by the cyclic ordering. And this is actually pretty important because in the finite case, indeed, these two things are the same, right? But in the infinite case, it's not quite clear what a face is. Think about the infinite graph Z, right? So I could draw it as a real infinite line that goes to infinity in both directions on the x-axis, and there it will be obvious that that there are 2 faces, right? The upper and lower face. But I can also draw it, so that it converges, right here. Up to a certain point, right? And then it looks like there is just one face to this graph, right? So in the infinite setting where the drawing may have accumulation points, it's actually not healthy to consider the geometric definition of a face, but it's much better to look at the combinatorial definition of a face. Okay. So we have Euler's formula, and since we're in a triangulation, every face has exactly 3 edges, right? So if I look at the number of faces, right, and multiply by 3, I got exactly the number of edges, but each edge I counted twice, right? From each edge appears in precisely 2 faces, so this equals 2 times the number of edges. 2 times e, and from this we immediately get that the number of faces, right? The number of faces is 2n minus 4, okay? By Euler's formula, where n is always going to be the number of vertices for me. All right. So how do we prove the circle packing theorem? We proceed as follows. So we first imagine that we know the theorem and that we have a circle packing, right? And our goal will be to compute the radii, right? So our goal is 1, compute a vector of radii for each vertex. So it will be R1 up to Rn. What does it have to satisfy, right? So if we have a circle packing, right, and these are, and this is a particular face, right? So this is one face, right? So the obvious thing that we see is that we can, let's say this is this center here. So this is the vertex I, this is the vertex j, and this is the vertex k, right? So we can connect the 2 centers, each 2 centers by a straight line, right? And if this circle has radii ri, right, this circle will have radius rj, and here we'll have rk and rj, and here we'll have another ri and rk. So we see that if we have good radii for a particular face, then these 3 numbers form a triangle, right? A triangle on which is edge length is precisely 2 times, ri plus rj, rj plus rk, and ri plus rk, right? And if we are given 3 numbers, ri, rj, rk, we are able to construct a triangle like this. For any 3 numbers, there exists a triangle like this, right? And we understand that if we look at we are able to compute these angles, right? These 3 angles just by looking at these 3 numbers, right? So for any, so our goal is to compute a vector of radii satisfying something that we will call star. And let's try to understand what star is. So given any Ri, Rj, Rk, right? There is a unique triangle with edge length right. So the only thing we have to observe is that these three edge lengths satisfy the triangle inequality, and hence there is a triangle satisfying this. There exists a unique triangle with these edge lengths, and hence, and so the edges, the angles at the vertex I, j, and k are determined uniquely by these three numbers. And so there is an angle. There exists a corresponding angle, angle at vi, vj, and vk. Right? We go over, for each face that we are supposed to draw three mutually tangent triangles. If we have a good choice of radii, even without a good choice of radii, we have these angles. But if the whole radii corresponds to a circle packing, right? Then, and this is a vertex that is not one of the outside vertices. Then then it has to be that the sum of angles at each vertex has to be 2 pi. Right? So this is the condition that we want. So let's say what should be satisfied. Right, so let's call this angle, right? If I have three vertices I, j, k that corresponds to a face, and a vector, so given r in the positive real numbers, right? For each face, f, which I think about as three vertices, vi, vj, vk, right? Define, right? The sum of angles, so this has, let's erase this face. Define, given a vector for each vertex, v. Define sigma v corresponding to the vector of radii r to be the sum of angles that you get from all the faces that contain v, right? The sum of angles at v corresponding to r. Right? So for any r, this is well defined, right? It doesn't mean the sum will not necessarily be 2 pi, right? If I start with a vector that is all 1, right, and I have a vertex, if r is all 1, and I have a vertex that is surrounded by 8, right, by 8 vertices, if the vector of radii is all 1, all of these triangles are equilateral, and the degree here will be pi over 3. And if I have 8 vertices surrounding me, then the sum for each vertex will be 8 pi over 3, and not 2 pi, right? And if we have a valid circle packing, so our goal, so star will be our goal, is to find r such that for each, so the sum of so that the sum of angles for each of the outside vertices is exactly pi over 3, right? So my goal is now to pack so that the 3 outside vertices are packed exactly in circles that have the same radii. Right? So if these have exactly the same radii, right, then no matter what is drawn here, right, the sum of angles will be pi over 3 on the 3 outside vertices. So sigma of vi, where's r? Sorry. Vi r equals pi over 3 for I, which is 1, 2, 3. And sigma v, any other v, is 2 pi for any other I. Otherwise. Right, so I understand that if there exists a circle packing, right, then such a vector of radii must exist, and we'll argue the other way around. We'll find this vector of radii and show that if we can find such a thing satisfying just this, then it can be drawn as a circle packing. Okay, is the strategy clear? Are there any questions about this? Okay, so it's a pretty naive thing to do. So first, perhaps let's see an argument, a nice, cute argument. Why, just with hand waving, why, if I have these radii, I can find such a packing, right? And the argument is depicted as in page 35 of your notes. It's a very nice argument that I heard from Ohad Feldheim and Ori Gurel-Gurevich. And it goes as follows. So intuitively, right, you given this radii, given this information, right, you just start drawing the circle packing, hoping that you will succeed. Right? So what do? You will start by drawing the 3 outer circles as circles of radius 1. Let me draw them very, very big. Right? So you draw the 3 outer ones. Right? You know, just because of this condition, you can verify that the 3 outer radii have to be equal. So let's just normalize them to be of size 1. Oh, by the way, notice that if I multiply this vector of radii by any scalar, this does not change, right? Because it just shrinks the triangle, and it's a similar triangle, right? So I start by drawing, right, the 3 right outside 1, 2, 3. I draw them as big circles. They're supposed to be equal. It didn't turn out. And now I look at the vertex that is just between vertex 1 and 2. Right? By the cyclic ordering, I know that there has to be. Its radius is given. So there's only one place. Its radius is, 1/10. It has to be tangent to both 1 and 2. So there's just one way one place to draw it. Right? You cannot draw it in any other place with the same radii, so it will be tangent to both of them. Right? You just put it the only place that it could be. And then you continue to the next neighbor on the right of this orange. Right? You know its radii. Right? So there's only one place to put it. Right? It has to touch the orange, and it has to touch 1. It has a fixed radii, so I can only put it in one place. Here. It must be like this. And then you continue. Right? And you continue this way. And the fact that the sum of angles at the vertex 1 is precisely pi over 3, assuming you manage to find such a vector of radii, that implies that when you finish all the neighbors of 1, the last one will fit exactly in here. Right? So this is something to verify. And also when you're inside, right, if you start drawing from the inside, you choose a vertex on the inside, you ignore all this, and you start drawing in a certain way, you can always see that you will not have any local intersections. Right? If I have one vertex of radius r something, and k other vertices surrounding it, right, such that you know that the sum of angles is exactly 2 pi, then this is easy to verify that there's always a unique way to put the circles around such that they are not going to intersect each other. So the algorithm will be simply to draw it like this and then continue from here to draw everything like here and so on. Right? And you have to, of course, prove, okay, so perhaps it's easy to observe that you won't have any local intersections, but it's not immediately clear that you won't have global intersections, right? Perhaps you're drawing things here, and somehow it makes you draw things up here, right? So it's unclear, right? But here's the argument that on page 35. So if I have this vector of radii, right, then for each edge of my graph, this is my graph with no circle packing, right? This is 1, 2, 3, 4, 5. So each edge of my graph receives a number, right? This will be the length of of its drawing in the circle packing, right? So this edge will receive the number R1 plus R5, right? Because eventually it will be drawn. Here is a circle of radius 5, and here is a circle of radius 1, and its length will be R1 plus R5. This will be R1 plus R2. And all of these lengths satisfy the triangle inequality for each face. So the claim is that if you have a planar graph with such assignments of numbers on the edges that satisfy the triangle inequality, then there's a unique way to draw it with straight lines. Okay? There's no circles here. Once I'm able to draw this graph so that this length is exactly R1 plus R5, this length is exactly R1 plus R2, and this is R1 plus R4, right? Then it means that I can put a circle of radius R1 here, right? R2 here, and R5 here, right? And everything will match exactly. So you just need to prove this general statement about having a graph with assignment of lengths on the edges that satisfy the triangle inequality. Then you can draw it by straight lines so that the lengths are exactly the labels written on the edges. And why is this true? You prove it by induction, right? So if your graph is just a triangle, right? This is the combinatorial drawing, and I have here 3 numbers, right, that satisfy the triangle inequality. Then it's clear that I can draw such a triangle, right? This defines a unique triangle up to rotation and translations, right? So what do you do when you have an inner? So now I have a big graph, right? And I want to use the induction hypothesis, and I know that the number of vertices is bigger than 3, so there has to be a vertex inside, right? I look at the picture, and the picture tells you what the proof is, right? This is your vertex inside, right? And coming out of it, there are a few edges, and you know exactly what the length of these edges should be, right? They have perhaps numbers, right? R1, R2, R3, not to be confused with the same R's here. So you start by drawing so each vertex corresponds to some polygon, right? You simply draw according to the labels written on the edges touching the vertex. You draw, just like on the left on page 35, you draw just the polygon corresponding to the faces that touch this vertex, right? So this will be, I have this one edge here, something like this. This polygon need not be convex, right? So this was some vertex V, right? I'm copying the drawing that took me a long time to make, right? Right, and these are the neighbors of the vertex, right? So let's call them V1, V2, V3, V4, V5, V6, right? So the fact that the sum of angles was 2 pi, right? So perhaps I did not say that in the general statement. Yes, I saw that you had a question. Sorry?
One edge to V4 is missing.
One edge to V4 is missing, right? So I realized that I forgot to mention the statement. I have to, if you have a planar, the general statement about drawing that I'm proving, if you have a general planar graph with labels with positive numbers on the edges, such that the triangle condition is satisfied, and of course you have to have the condition that when you calculate the angles at each, according to the cosine law, right? Each triangle, you know exactly what the angle should be. If you know that for each internal vertex the sum of angles is 2 pi, then there is a unique drawing, right? And the 3 other vertices have some 3 angles that sum to 2 pi. And let's take pi over 3. Then there exists a drawing that is unique up to translations and rotations, right? So I I'm sorry, I forgot to say that. But this input has to be used exactly in this point. You start from an internal vertex in your induction, and you draw the edges coming out of it, and you are able to compute these angles. So you know what this angle is, and this angle is, and this is how you draw. So you understand. So it has to fill a full circle because your input is that the sum of angles at this vertex is exactly 2 pi. So there is a polygon like this, and these edges inside are the internal edges. And now you want to get a graph with labels that satisfy everything that I said that has one vertex less. So what you do is you erase this vertex and all the edges touching it, right? But you keep everything else and all the labels. And now you use a nice fact from high school geometry that is sometimes called the two-ear theorem. Two-ear theorem. It is very easy to show that every polygon in the plane can be diagonalized. So I can add edges that connect vertices on the boundary of the polygon such that every face now becomes a triangle, right? And this is depicted in page 35 on the picture on the right, right? So you knew exactly where these vertices were drawn, right? You know exactly their coordinates. So you know exactly and you know exactly all the lengths of this polygon. This is an honest-to-God polygon drawn in the plane. So you can calculate the lengths of these purple new lines, right? So I calculated all of these lengths. And now I have a new graph, right? There's an outside graph that I've just replaced, just removed one vertex, added some edges, and everything stayed the same in the original graph. And it's still, so I have now new labels on these edges, which determine their length. And just by the drawing, you see that the sum of angles of each vertex has not changed, right? This is just a proof by the picture. And now you use the induction hypothesis. You know you could draw this thing, right? And if because it has one vertex less, right? You draw the graph that has one vertex less, and the polygon corresponding to the neighbors of what the vertex was here has to be drawn exactly in the same way, right? Because I know exactly all the lengths and all the angles of this polygon, so it has to be drawn this way, of course, up to a translation. Right? And now I go back to the original picture. I erase these purple edges. Right? And now, because of the induction hypothesis, the rest of the graph is also drawn here. Right? I'm not drawing it, but it's there. And now I add the vertex and put it exactly in the location that it was before, and add all the edges that I had before. And this gives you a drawing. And this is also an algorithm for how to draw the drawing given that you have these vector radii. Okay? Well, I hope this was convincing enough. If not, you can read the details. Well, any questions about the...
Why do you call it two-ear?
Oh, two-ear because when you have a polygon, you add, so you have one ear here. As you can see, right? This is an ear. No, and the other side is another ear. It's not me who calls it this way. It's Wikipedia, the all knowledgeable mathematician. But this is how it's known in the theorem. But it's a classical thing. But if you're not convinced that this is an ear, then we have different ideas about anatomy. Yes. Okay, so any other questions about this part of the proof? So I hope I convince you that the difficult part, or not the difficult, but the part that we need to do now is to find this vector of radii. And how do we do that? So first thing, so now we can forget about the rest of the argument, and we continue here, right? And the one thing that we understand is that for any r of positive, for any vector of positive radii, I get for each vertex and each face, right, an angle, right, a number between 0 and 2 pi, which represents this drawing. If I would have drawn it by the circles corresponding to the three radii of the face, there would be one particular angle, right? And of course, these could be, crazy angles that don't represent any circle packing, and if this is satisfied, then the argument that I told you should be convincing enough that this is that there is a drawing. And obviously, you can imagine that I can write a formula for this angle. Would anyone like to see the formula? Right. Yes, let me write to you a formula of this angle, right? Just so you will know that it is possible. I worked very hard to figure out this formula with my high school notebooks. It's just the cosine formula, right? If you know the lengths of an edges of a triangle, you know all the the cosine of the angle of Vj, Vi, Vk, right, is, and you don't even have to write it, we will not use this formula. Corresponding to the three radii is 1 minus 2 Rj, Rk divided by Ri plus Rj, Ri plus Rk, right? And you look at the unique number that is between 0 and pi. Right, the only reason I've written this formula is to convince you, firstly, that this quantity is computable, and secondly, that obviously it is continuous in the radii, right? If I change the radii a little bit, the angle changes by a little bit as well. And what we really need is the following simple observation, right? So the observation is, so again, I have a vector of radii, and then for each face and each vertex I have an angle at that vertex, right? And then for each vertex I have the sum of angles at this vertex. And the first thing that we note is that, so the first claim, not a claim, let's observe that if I go over all the vertices and sum their sum of angles, so how did I write this? Vi r, and I go over all I from 1 to n, right? Then this equals 2n minus 5 times pi. Okay, so no matter what, and this is true for any vector of radii, not just the good vector of radii. And why is this true? 2n minus 5 is the number of internal faces. So this is a hint why this claim is true. And now we see no matter what the vector of radii is, I go over each internal face, right? No matter what these numbers are, and so no matter what the angle is, so each face corresponds to some triangle, and the sum of angles in triangle is pi, right? And eventually, so when I sum over each vertex the sum of angles, it's like going over each, it's summing it in a different order by going over each triangle and summing all of the angles there, right? So it's the same. So it's the same thing. So this is good because no matter what R is, and I'm going to change it in certain ways, I have something that stays the same. Okay, so this is tempting. So it's tempting to perform the following thing, and this is a pretty standard thing. So the algorithm will be: I'm going to choose some radii and change them, right, and hope to make this sum closer to this. This sum is always this, and I hope to make to make this closer, to make these closer to this. So let's define, instead of the sum of angles at each vertex, let's define the defect of a vertex. By the defect, I mean how far it is from what it's supposed to be. Okay, so let's define delta VR, right? So this is a definition. This is going to be sigma of VR, right? When V is an inside vertex, so V not in 1, 2, 3, minus 2 pi, sorry, right? So, and sigma VR are minus pi over 3 when v is one of the 3 outside vertices, right? So my goal is now to find a vector of radii where all of these is 0, right? I don't know if this is the most natural thing to do, but when you have this type of thing where you want to control a functional of a vector, right? And you want to minimize a positive functional, and you want to minimize it, right? You want to get it to 0. This could be not to minimize it, to find a point in which it is 0 precisely. It's natural to look at the sum of squares of these things, right? So this is some way of controlling the errors. And then I will define this E to be the sum over V, right, of delta VR squared. Right, so if I manage to find a vector of radii such that this quantity equals 0 precisely, then this is exactly what I want. It implies that all of these numbers have to be 0, right? And everything works fine. Okay, so so now my goal is to present to you an algorithm that you iterate it. Each time you change the vertex of radii according to some prescription, and this makes this error term go down every time by some constant fraction, right? So it will converge to 0, and then there will be the issue of seeing that the radii, each coordinate does not converge to 0 or to infinity. Okay, this will be not very difficult, but there's one key observation that we need to use that somehow controls this whole thing. So you will notice that what I'm about to write now is the only thing that we really use about the geometry here. And this is in fact some sort of a general algorithm that works in many other cases. So here is the key observation. Okay, so so consider a face. Vi, Vj, Vk, and assume that I have assigned it 3 numbers, and radii Ri, Rj, Rk. Right, I want to change these radii, and I want to see what is going to be the effect on the angles. Right, so this is the key observation. So if we increase Ri, right, and leave but decrease or not change or leave unchanged Rj and Rk, what happens to the angle at I? The angle at Vi, right? Let's draw it. That's the only proof that we can have here. If I have these 2 circles R, J, and Rk, right, and I have Ri here, right, and now I make the white circle become smaller and smaller, but it still is tangent to J and K. So what happens to the angle?
Is the circle becoming smaller?
The circle, oh, sorry. I'm increasing it, but leaving, sorry. So I'm making Ri bigger. So what happens to the angle? It decreases, right? As it becomes bigger and bigger, this becomes, a smaller angle than this. And here is the proof of this fact, right? This angle is bigger than this angle, right? Then the angle at Vi, the angle at Vi decreases. and also the other way around, right? So if if Ri and Rj grow, but Rk decreases, right? So Rj, so now it's the same thing. If I decrease this, then the angle actually increases. Sorry? So let's make it just so it will be the same thing. So if Rk and Rj grow, but Ri decreases, then the angle at I increases. Right? So we have a certain monotonicity property that we will use throughout this algorithm. Right? Is this clear? This is a completely elementary and trivial. So what is the algorithm? So let's describe the algorithm now and talk a little bit about its talk as much as we can about its analysis. So the algorithm is as follows. So we start with a certain vertex. So we start. Let's start with not a vertex. We start with a certain assignment of radii, and I always want to normalize, just because it will make my life slightly easier. I always want to normalize so that the sum of the radii is 1. Right? I can always multiply each vector of radii by any scalar, and that will only correspond to a dilation of my picture. Right? So I start with R0, R0, just to be the vector 1 over n. But I will always normalize it this way. I start with such a vector, or in the ith iteration of the algorithm, I will have such a vector, and that one corresponds to a vector of defects, right? And we see that because I've subtracted exactly the right thing, the sum over the vertices of the vector of defects is exactly 0, right? So this we see exactly from here, right? The sum of delta v r naught over v is exactly 0, right? I have 3 internal vertices, which give me exactly pi, right? And then n minus 3 3 outer vertices that give me minus pi over 3 to each one, and then n minus 3 internal vertices that give me minus 2 pi, right? So you add these two things, this cancels exactly this 2n minus 5 times pi, right? So the sum of the vector of defects is always 0, and our goal is to find the radii such that this sum of squares is 0. So I start with one particular vector, and I order the set. I look at the vector of defects, L, V, R, 0, right, or Ri, right, at each iteration of the vertex, at each iteration of the algorithm, right, and I just order it and draw it on the line, right. So this is the real line, and for each vertex, I draw exactly where the defect is. So let's draw it this way. Perhaps there are several defects that are the same. That's fine for me. Right, this is I just plotted the vector of defects, right? These are all real numbers. They could be negative. And I know that 0 is somewhere inside because their sum is 0, right? And now I choose, let's add some more here, right? And now I choose the largest gap in this drawing. Okay, so I look at the largest space. I look at all the spaces between the blue points, and I choose the largest gap. So in this drawing, it will be this one, right? So this is the largest gap. Right, and right, I choose the largest gap, and I call all these vertices that their defects are large. I call this set S, and this set I will call V minus S. Right, these are the set of vertices. Right, so in particular, right, so the algorithm choose the largest gap. Choose largest gap. The fact that I choose it to be the largest will only be significant in the analysis of the algorithm. Afterwards, I choose the largest gap, right? And let S be S, and V minus S are as in the picture. Are what's the vertices to the right and to the left of this gap. To the right and left of this gap. To the right and left of the gap. Right, so in particular, the minimum of the delta over all the vertices here is strictly bigger than the maximum of the defects over all the vertices here. Right, so now what is my algorithm? It is the following. So for some lambda in 0 and 1, and I will tell you what this lambda has to satisfy. I change, right? I need to create a new vector of radii. I change Ri. Ri goes to lambda Ri if I is in V minus S, right? And otherwise, I leave it the same. I and S. So, and this makes sense, right? So for all the vertices here, I'm going to leave the radii the same, right? But to all the vertices here, I'm going to make the radii a little bit smaller, right? By some lambda that I will tell you exactly what it is. And this has the effect by this key observation, right? When I make something smaller, the angle grows, right? If it is smaller, yeah, we have to check this exactly. The angle grows. So this will move all of these defects to the right. And all of these defects will move to the left, right? And they move in a continuous fashion as I choose lambda. And my goal is to show that I could choose a lambda between 0 and 1 so that these 2 points meet exactly, right? So that it's not monotone. So it's not clear that the order between, as I change, that the order between the defects remains the same. I don't know. Perhaps this one will move so fast here, and this will be the first one. But I want to move all these things to the right until they meet. Right? And I have to convince you that they meet. That firstly, I have to convince you that these indeed, all the defects move in the right direction, and that there is a point strictly between 0 and 1 in which they indeed meet. Right? And this will be some continuity argument. So what do I want? So for some lambda, what is the lambda? So we find lambda strictly between 0 and 1, such that after the change, right, the vector of the maximum over a vertex, the maximum over a vertex in V minus S of the defect of R, let's call it I plus 1, or I'm calling it V R I plus 1, equals the minimum when I look at all the vertices on the right. Minimum of V belongs to S of delta V R I plus 1. Right, so I need to show you that this exists and that you could choose such a thing and that everything works in the right way. Okay, so and this is the algorithm. And then afterwards, what I need to show is that at each iteration of the algorithm, that this quantity right, drops by a multiplicative constant. Right, it's the E of R prime is smaller than 1 minus epsilon, the original E. And this epsilon will depend on the number of vertices and edges of your graph. Right, so is the strategy clear at this point? Okay, so let's try to convince ourselves that this is true. So first, let's try to convince ourselves that indeed the gaps are moving in the right direction, right, after you make the change. And this will follow just from this observation, right? So well, this is the bad eraser. So the first claim is that the gaps, or the defects, move in the right direction. In the right direction. Let's observe that. So let's consider, let I, sometimes I confuse I and VI, but it should be clear. This is just a vertex that is left of the gap. So it belongs to V minus S, right? And I'm performing this algorithm. So there are several cases, right? So let's look at and consider a face which I belongs to. So let's call it I, J, K, right? So I belongs to some face, I, J, K, and I don't know for sure if J or K were in S or in V minus S, right? And I want to show that not only the sum of angles at I increases, right, but also, right, because it needs to move to the right, the defect at I, but also that each particular angle of each face that it belongs to also increases. Right? It makes sense, right? These are the big vertices, right, the big circles, and I've shrunk them a little bit, right? So the picture is that perhaps in Ri this was too big, right, and I didn't have enough space, or I didn't have enough space to surround them, so I want to make it smaller so that they will fit more snugly in. So there are a few possibilities according to what happens to J or K, right? So there are three cases, right? So let's check each case in particular. So the first case is that both J and K are in V minus S, right? In this case, I multiplied both Ri and Rj and Rk by the same constant lambda, so the angle has not changed at all at this face, which is fine. Right, so in this case, angles have not changed. Right, so in the second case, case 2, right, what is my case 2? I is in V minus S, but J and K are in S. Right, so what happens here? So in this case, right, where's the picture? Right, in this case, I has become smaller, right? But J and K remains exactly the same size, so the angle has decreased, and we're fine. Right, so angle has increased. Right, I'm making I smaller. Lambda is between 0 and 1. Right, so angle at I increased, which is the right direction. And the third case is that so third case, right? I is in V minus S, and J is in V minus S as well, but K is in S. Right, so in this case, I'm decreasing the radii of I and J. So let's draw it here. This is I, this is J, right? And this is K. And I'm decreasing both Ri and Rj's, right? So the new picture will be this is K, and these two are very small, right? But moving from this picture, I can also dilate back, because I multiplied Ri and Rj by the same number, right? It's the same thing as multiplying the radii of K by 1 over lambda, right? And you get the same angles. So it's the same thing as increasing K, right? And it's the same thing as just increasing K and leaving the radii of I and J the same thing, right? And as you do this, you see that the angle here has to grow, right? This is also a part of the observation, right? Because this thing goes more down. Okay, so case 3, so this is same thing. So this is has the same angles, same thing as taking multiplying Rk by 1 over lambda and leaving Ri and Rj unchanged. So the angle at I increases, also increases. Okay? So this is completely elementary, and there's absolutely no formulas in this proof, right? There's nothing to do here. And so I convinced you that all of the defects of V minus S go this direction, and all of the defects of S go in this direction. Okay, I didn't write it down, but it's obvious that it's exactly the same argument from the other side. So they all go in the same direction, and what I have to convince you is that I could choose a point lambda, right? And obviously this change is continuous, right? And so I need to convince you that I could choose a point lambda such that these two, the minimal defect here meets the maximal defect here as I change them. Okay, so and this will complete the definition of the algorithm, right? Just to show that you can find such a lambda. So let me leave the definition of the algorithm here and continue here. So I want to show, so I proved to you that the things move in the right way, but I need to prove to you that I can find this, right? And indeed, I have to be careful, because what if I move them in the right direction, but only as lambda approaches 0 do they exactly meet, right? 0 is not a good thing, because I don't want to have ever any radii that is 0, right? I want the circles to be drawn as real circles and not as points. So I have to convince you that I can find such a lambda, and here is the argument. Right? It's surprisingly, it's a similar argument. In fact, all of these arguments is essentially one argument iterated again and again. And here is the claim. The claim is that the limit as lambda goes to 0 of the sum of defects I belongs to V minus S. The sum of defects on the left of delta V I R, let's call it R lambda. Okay, so right, if I had performed this change with a particular lambda, so let's call this R lambda here instead of R I minus 1. Right, lambda is the new, R lambda is the new vector of radii after I perform this. Okay, so this limit is bigger than 0. Right? Why does this give me what I want? Right, so I know that as lambda goes to 0, if I sum the value of all the blue points on the left, it gives me a number that is bigger than 0. Right? But we know that the sum of all the blue points is precisely 0. Right? So if this sum was bigger than 0, that means that this sum has to be smaller than 0. That means that the two things have already crossed. Right? If they have crossed, that means there was a point earlier that they just meet, because everything is continuous in lambda. Right? So this is enough to prove what I want. Right? So this is in remark, this is enough. So the limit as lambda goes to 0 of the sum of I in S of the delta Vi R lambda is smaller than 0, and so there is a lambda that they just meet, and so a lambda that we want, and so a good lambda exists. Right, in 0, 1. right? Not at 0, because the limit is going to be strictly bigger than 0, right? It's going to be something like at least pi over 3 or something like this. So it's not something strict. Okay, let's prove this. And it's, again, you will see that it's a very similar proof, right? So, right, so I'm looking for each I in Vs, I'm looking at the defect of the sum of angles at each I. So let's look at a particular I. So what do I claim? So here's the proof of this claim is the following. Consider a face ijk. Some of its vertices may belong to S, some of its vertices may belong to V minus S, or perhaps all of them are in S. I'm just looking at one particular face, and I'm claiming that if I look at the sum, then as lambda goes to 0, right, the sum of angles, let's continue here because it's hard for me to. The sum of angles at the vertices corresponding that belong to the left to V minus S, this sum of angle converges to pi as lambda tends to 0. Okay, so let's see what this is. The sum of angles at vertices of the face that belong to V minus S converges to pi. Okay? Let's just see why this is true. So, well, I guess, if ijk doesn't have any vertex that belongs to V minus S, then there's nothing to say. If all of them belong to V minus S, then for any lambda, the sum is exactly pi, right? For any lambda, it's exactly pi. So obviously, the limit will be pi. Let's look at the one case, right? So case 1 that is non-trivial, that you have one vertex belongs to V minus S, right? And two other circles that belong to S. So their radii does not change. And you can see that as you make this circle smaller and smaller, right, it becomes teeny, teeny, weeny, and the angle at it becomes close to 180. Right? This is obvious. And also the second case, I apologize, I'm getting tired and it's hard to write. But all of this is written in your notes, and also this is completely trivial. And the proof is it's exactly the same words as I wrote before, with the same picture. So the other case is where you have one vertex that belongs to S and two other vertices that belong to V minus S, right? So this will be this and this. So this is how it looks like. And you see that as you shrink them, right, they become smaller and smaller. This angle becomes closer and closer to 0. So that means that the sum of these two, right, becomes equals to pi. Not each particular one converges to pi over 2, right? Because they can have originally some different radii, and you're multiplying them by the same constant. So this one could be pi minus pi over 2 minus something, and this would be pi over 2 plus that same something, right? So it's not that this angle converges to pi over 2, but just that the sum converges to pi, right? So you get this. What do we learn from this? What do we get? We get that the limit as lambda goes to 0 of this quantity, right, of what we want. So the limit of the sum as I belongs to V minus S of the defects, or let's not write the defects, let's write the sum of angles, and afterwards we'll subtract. The sum of V minus S, the sum of angles at the vertex V corresponding to the vector of radii R lambda. So for each vertex, we saw at each triangle, we saw that the vertices corresponding to v minus s, right, they add to pi, right? So this limit as lambda goes to 0. So this will be pi, right, times just counting the number of, counting for each triangle that you have, each triangle, each face that has a vertex in v minus s will contribute precisely pi, right? So this is exactly what I have here. Pi times the number of faces that have a vertex in v minus s. So let's just call it f of v minus s. Right, so this thing is the faces that contain a vertex in v minus s. Right, so this is it. And now let's try and analyze. This is the geometric thing that we wanted to do, and now this is just a combinatorial analysis of what could these numbers be. Okay, so let's look at a few examples and see that this gives us what we want. Okay, so shall I erase this? No, I'll just continue. I'll just continue here because so you can see what the algorithm is exactly. Right, so let's look at a few cases. What happens if what happens if let's say if v minus s, its cardinality is wait, am I looking at the wrong place? Yes. Sorry. This is where I always have a mistake in this error when I prove it. I always have a mistake when I prove it. The full proof appears in the notes. So let's see. Let's work out this way. Let's do it. Right. So let's look at the complement of f of v minus s. Right. So let's look at f. Complement, these are all the faces in which all three vertices, so that all three vertices are in S. And by the way, you should note that in this in this definition, I should have said internal vertices, right? Because the outside face is not counted in all of this thing. Right, so let's look at the complement. Right, the number of faces is 2n minus 4. I'm only looking at internal vertices, so the sum of these two cardinalities is 2n minus 5. Here I'm also only looking at internal vertices, internal faces. Sorry, not the outside face. And let's look at the case. You know, if f hat, right, is smaller than 2s minus 5. Right, so this is faces with all three vertices are in S. So what we get in this case is that f of v minus s, right, is bigger than 2 times v minus s. Right, the sum of f bar, the cardinality of it, and f of v minus s is exactly 2n minus 5. Right, so if this is smaller than this, then this has to be bigger than this, right? Because their sum is exactly 2n minus 5, right? And if this is the case, then we get that that what we have written here is strictly bigger than 2 pi minus the cardinality of the set, right? And in this case, because the defect, right? In this case, we get what we want because the defect subtracted from the sum of angles at most 2 pi, right? And because we have here strict inequalities, right? This will be also bigger than 0. So in this case, the limit of the defects, of the sum of the defects in the usual, and what we, I think I'm writing it this way, right? Is bigger than 0. Right, so this is one case. So you can think about this case as this is the case where, for instance, V minus S is a set that is deep inside the graph and doesn't contain any of the outside vertices, right? So if you have, and when you look at this quantity, all the faces that 3 vertices are inside S, this number is the largest that it could be, right? Because when you look at the graph spanned on these faces, in the largest scenario, it's the entire graph, or it contains a triangulation on S, and then the number of internal faces is exactly 2S minus 5, right? So this number, this cardinality cannot be bigger than that. So this is the worst case scenario. So there's 2 other cases in which you have here equality, and then you split the cases according to the outside faces, and you check that indeed one of the outside faces has to be contained in this set. Otherwise, you get some sort of a contradiction. So I leave you to read these in the notes. This is just a combinatorial analysis of this thing, and you get the proof of the previous claim. Okay, so this is not difficult. Whew. All right. If I'm tired, I guess you guys are, more tired or very aroused because you haven't.
One question?
Yes, please.
What's the special role of the choice of the largest fact?
Okay, I haven't discussed this yet, so let's discuss this now in 10 minutes. I said that the choice it comes only at the analysis of the algorithm. So let's say a few words about the analysis of the algorithm, right? So except for this part, which I haven't finished to you, I haven't finished what we have convinced. I am convinced. It is up to you how you feel about life and this proof that you can find such a lambda in which everything is exactly as depicted. Okay, so the rest of this proof is really not that difficult, right? So the question is now, so we could do this. How do we improve? So now we have to consider. So we have this algorithm. This algorithm works, and let's say a few words about its analysis. Right? And this is where the largest gap will come into place. So perhaps I'll still leave the algorithm here and erase this. Is it okay, or it's all in your notes, so I think it is fine. And perhaps one word about the algorithm is that I have to, after I perform this change, I can always normalize what I got to have the sum of radii to be 1. This is fine because I'm doing this so that no radii will escape to infinity in this process. Okay, so if I'm reminding you that this E was the sum of the defects. Yes, I wrote it the other way around. Square, thank you. Right, so this is after Ri, right? And I'm writing E prime or let's say R, for the sum of the defects after one iteration. Sum of the defects square after one iteration of this algorithm, right? And I want to show that the difference has become smaller, right? So let's try and do this analysis rather quickly. So I'm looking at E minus E prime, right? This is after one iteration, right? And I want to show that this is that I've improved, right? That this is smaller than 1 minus something times the original E, right? So this is the sum of delta V. So now I'm writing delta and delta prime instead of delta R and delta R prime, right? So minus delta prime square. Right? And this equals, let me first write down the equation. This equals to the sum over V of delta V minus delta V square minus delta prime of V plus 2 times V T minus delta prime V times T minus delta V. Okay, t minus delta prime v times delta prime v minus delta. Okay, what is t? I didn't tell you what t is. T is exactly this point. The point that they meet for the first time is, I'm calling it, this is a point on the real line. This is called t. So now let's just verify that there is indeed equality here. So when I open the parentheses, I have here plus delta square, which corresponds to this term. I have here a plus delta prime square, which does not correspond to this term. Right? But here, I'm using the fact that the sum of the deltas is always 0. Right? So when I open these parentheses, I have t times delta prime v, the sum over v of that is 0. T times delta v, the sum over v is also 0. And then I have minus delta v times delta prime v times delta prime v. That gives me precisely minus delta prime square v times 2, right? Which gives me exactly this term, because I had here 1 times delta prime square v. And then the cross term is exactly 2 times delta minus 2 times delta prime times delta v, which is exactly the cross term that you have from here. So I just rearranged this equality. And now, when you look at it this way, you see that this has to be positive, right? That this difference has to be positive, right? Because here I have something positive written, and now here I'm looking at t minus delta v. So if v is such that t minus delta v is positive, right? That means that v is here, right? Just to the left of t. Then that means that delta prime v is also smaller than delta v, right? Because this was the first time that they met. So this point is somewhere here. Perhaps it's exactly this point, but delta v is at this side. So they will both be, so if this was positive, this is also positive. And the other way around. If this is negative, this also has to be negative. So you see that just by writing it this way, we understand that the sum of squares decreases. Right? This is just that. So now, and why does it decrease by a fixed proportion? Let me just do the analysis here. It's not very difficult. So here is the only place where I use the fact that I used the largest gap. So this is right. So let's finish in 2 minutes. So e minus e prime, right, is bigger than delta u minus t square plus delta v minus t square. And this is true for any u and v, such that u is in s, and v is in v minus s. Right? So this way I'm allowed to choose, and this follows just by this inequality. So I'm allowed to choose the u and v that makes this optimal, right? And this is always bigger just by the analysis, by the difference delta u minus delta v square divided by 4. This is at least what I got, right? So the only thing that I use about the so now I'm allowed to choose, right, this so that this is bigger than the maximal, than the gap, right? So in the let's finish here. Thank you very much.